Hi guys, so today is our sixth day of the lecture. Let's review let us review what we learned in the last lecture, okay? And then so today's plan is we'll review some materials we learned last time in the last lecture, and then we'll work on some of the new materials, and then we'll also look at some of the questions that would help you review with the exam one, okay? But then I'm not planning to make a too long video for today. It's gonna be pretty short, so you guys can work on more, homework and on the homework problems, as well as study for your exam. So we won't take all 1 hour 25 minutes today. We'll make it quite shorter, so you spend some time practicing for exam as well as completing your homework, okay? Alright, so in the last lecture we learned about physical pendulum, right? So we said physical pendulum is any object which oscillates back and forth in time, or which has a repetitive motion, and which has a mass extended along its length, right? And then we looked at the frequency of a physical pendulum F equal to square root of what? I should not forget this 1 by 2 pi mgd by I, right? And then we said mass is the mass of the pendulum, d is the distance from pivot to the center of gravity, I is the moment of inertia of that object, okay? That is for physical pendulum, and physical pendulum is one of a system that exhibits simple harmonic motion. We also, after we are done with the pendulum, we started learning about damping oscillation. And then we said we could use a mathematical equation, a mathematical model to describe the damping oscillation, where we looked at the equation, and it turns out to be, for the equation for position versus time is xt equal to what? A e to the power minus t over tau cos 2 pi f times t here, right? A is the maximum amplitude of oscillation. We said this tau is what? Tau is time constant, are also called as characteristic time. They are characteristic time of decay of oscillation. Okay, so tau is important, right? We also we did some of the problem, one of the problem related to it. And then F is the frequency here, and then E is exponential, right? Like here, E has the 2.718, that's the value, that's constant, right? So this is the equation that can be used to model the position versus time motion of the damping oscillation. What else? And then we looked at some of the examples, right? I'm going to erase this part here. And then we looked at a couple of examples here, how we might be, when would might damping be a good thing in a mechanical system. We said, it's useful in automobile for shock absorbing purpose, right? We also looked at the example where we could use it for a mountain bike also. So this is our topic today. Next topic. So I'm going to erase this part here. We touched a bit about this, but we are going to look at it today. So how do we overcome damping in a mechanical system, right? So it does have a usefulness, right? Damping is useful, but it may not be good in every system. So we may have to, we may not want damping in all the mechanical system. There may be cases where, we don't want damping to persist. So how do we overcome damping? So damping has to do with what? Some sort of loss of energy in the system, right? So what do we say is, if energy is lost, then what do is we could just add, energy from external system so that the damping is overcome. Okay, so alright, so this brings us to a topic, today's topic about driven oscillations. Right. So to overcome damping, you can add energy into the system. Okay. Remember I showed you guys a cup of water and then how it has certain oscillation, and then if we apply external force, then you can see the system is going to have a different oscillation, right? So actually, you know what, let me show that demo again today, so just a moment. Alright guys, I got this cup here. So I have a water, right? So this system has its own oscillation frequency, okay? So it has, meaning it has certain energy, right? And then now if I apply external energy, then it's going to bring some changes in the system, right? But now we said, like if this water was moving or it was oscillating itself, and then now I apply external force to oscillate, then what happens? It's gonna respond it in a different way now, right, with the external force. So there is this thing called natural frequency, also known as resonance frequency. In this context, okay, in the context of driven oscillation, natural frequency of the system, and it is represented by F naught. Okay, so meaning this has a certain natural frequency on its own, like it oscillates at its own natural frequency. Now, this is just a little bit here, so I'm going to put this way over here. Oops, I don't want that here. Okay, how about this? That is the F naught, okay? So it has its own frequency here, this system, if I am not applying anything here. That's the natural frequency at which this, system oscillates here. Now I use my hand and then I apply external force, so let's do this. External force, right? I have it here, sitting here, it has its own oscillation. We may not be able to see it, but it is, you know, right? A lot of things are changing here. So now if I apply this, what happens? I'm applying external force. So now, see, it's responding in a different way than before, right? Now if I apply more, look at that. Okay. So depending upon the external force I'm applying, this system behaves differently. Okay. So the frequency of the external driving force is called driving frequency. Driving frequency F, right, okay. So this is the frequency associated with EXT, or external driving force. Right? Driving frequency that drives the system really. The frequency at which it drives the system basically. Okay, so driving frequency F. So F and F naught are different, right? But then how will this system really respond really depends upon these two factors: natural frequency or resonance frequency of the system, and then driving frequency. So this system here, if this system happen to have a condition where the driving frequency from external driving force is very close to natural frequency of its system, then there is going to occur very, very large oscillation. Okay, so condition for resonance, this situation is called resonance. Okay, condition for resonance is when we have F equal to F naught are very close to each other. Okay, so maybe, yes, so that's the mathematical condition. When the natural frequency of the system or resonance frequency of the system is equal to or very close to driving frequency of the external driving force, then the whole system will go under very, very large oscillation. So what are the implications of that? So what happens anyway, if the system goes through very large oscillation? Look at this, right? Even here, if this system goes to very, very large oscillation, we don't know what happens. It may even be capable of breaking this cup if it is large enough. Okay, if these this frequency match or the condition for resonance is achieved, it is possible. Okay, so I'm going to erase this part here. Okay, so this condition for resonance so you may have heard about the story of a Tacoma bridge, okay, like how the Tacoma bridge was destroyed. So look at this here. It has to do with the condition for this resonance. Okay, so Tacoma narrow bridge here. You see there is this bridge, and then you see there is So this system has its own natural frequency F naught. But then what happens is so many cars and then trucks and so many vehicles keeps moving. So every time they move, what happens? They're supplying energy, right? Like the external energy. So those vehicles are driving this system at certain frequency, right? Because when they move, they drive it in this whole system in a certain different frequency. So now, when the frequency of the oscillation of this bridge, natural frequency F naught, is very close to the driving frequency due to external driving force, boom, right there, look at this breeze is totally destroyed here because of very large, it's a very large oscillation. So see, this breeze is just up and down, and because such a large oscillation occurred there, this breeze was destroyed. Okay, so it's very important, like, you know, to account this condition for resonance. Another example is something called acoustic resonance here. So here is an example of one wine glass that's destroyed. So wine glass are, you know, they have their own frequency. Not just wine glass, every system has its own natural frequency, okay? But we are just taking this here because these are some of the famous examples. So it has its own natural frequency. You don't even have to touch a wine glass if you want to break it, actually. Acoustic resonance means if this object, you know, if wine glass has its own resonance, natural frequency, and then if you made a sound, that will sound so that this system, wine glass, is driven at the frequency equal to its natural frequency, then again the large oscillation occurs. Now, of course, in the wine you may not see large oscillation occurring, right? But if this condition for resonance is met, we can just break you know, wine glasses without doing much work. Okay, so very important condition for resonance. All right, so with this, we are actually done with this second chapter of this semester. So this is our chapter 14 in oscillation. Whatever we learned so far, this is going to be very important for next chapter. Next chapter is about traveling waves, and we are going to start that on Tuesday. Okay, but now for next video, I'm going to do a little bit of you know, give you guys a little bit of review for exam 1. All right.